Hey guys, my name is Demetric McCall. I am a biology major with a minor in chemistry. Okay, hope everybody's doing well. So for this research, I've collaborated with Rebecca Reid and Dr. Adogla. The basis of our research is to design and synthesize fluorogenic naphthalimide-based Triazoline dyes. It's a mouthful, so that's in the title. Mhm. I will briefly read over the abstract and introduction, then I will discuss some of the chemistry and important applications of this synthesis. Okay. Fluorescent dyes are important tools in medical, biological material, and environmental research. Advances in chemistry and the development of new dye probes have been the basis of many detection techniques in these fields. In this work, we are designing and synthesizing a number of novel 1,8-naphthalimide-based triazoline dyes for application in bioimaging. Triazolinediones are very reactive dienophiles that will serve as the point of covalently linking the dyes to specific targets, as well as modulating the fluorescent dye. 1,8-naphthalimide and its derivatives are one of the classes of dyes commonly used in fluorescent sensing. Their fluorescence properties are easily altered by simple modification of the dye with other functional groups. For fluorogenic probes, the design requires attaching to a fluorophore, attaching to a fluorophore, sorry, a functionality that quenches fluorescence but transforms into another functionality which restores the fluorescence after selectively reacting with its target. This method has been successfully used in fluorescent sensing. In this work, we hypothesized that linking the fast reactive dienophile Triazolinedione to naphthalimide dye will be useful in modulating the fluorescence of the dye and can be applied in sensing conjugated diene containing molecules. So this reaction between the dienophile triazolinedione and the diene is called the Diels-Alder reaction. So generally speaking, diene and dienophile reaction is called the Diels-Alder reaction. So the Diels-Alder reaction is a reaction between a conjugated diene and an alkene, usually called a dienophile. So they love dienes. Dienophiles love diene. So to form a stable cyclohexane. In our design, we propose to modify a 1,8-naphthalimide with a fast reactive dienophile triazolinedione for application in sensing biomolecules such as lipids, vitamin D. So very important, at least potentially very important. So drawing back to our hypothesis, we have here our dienophile, and this right here is a diene. You see two double bonds, just two alkenes or whatever you want to call it. It's a diene. And this is like the general structure of the triazolinedione. You see the two ketones right there, and then some R group like branching off to the side. So in this case, our R group is the naphthalimide molecule. Basically this part right here, which is consistent all the way through. And ultimately we want to get this molecule. Have the dienophile part here. Well, you have the triazolinedione part here, and that some R group is our naphthalimide molecules. This part. Okay. Again, this entire molecule will serve as our dienophile. It can react with a diene right here. So you have a fluorescent molecule. That's our goal. We want to get something like that. So say we want to. So that means we haven't finished yet. So we have two more steps left, to complete the synthesis of this molecule. Naphthalimide triazoline dione. Well, I'll tell you, this is a mouthful to say that naphthalimide triazoline dione. That's a lot. So one very important thing I want to take note of or pay attention to is this right here. This is a profluorophore, and we expect it to be non-fluorescent or weakly fluorescent if it is fluorescent at all. But as soon as it reacts with this diene, then we want it to be fluorescent. So you may ask, what is a fluorophore? Okay. So what a fluorophore does is basically it absorbs light energy of a specific wavelength. That light absorption results in excitation of electrons in a specific fluorophore molecule. These electrons don't stay excited forever though. In fact, very quickly the fluorophore re-emits the absorbed light energy at a longer wavelength, so it'll be a different color as the electrons return to their basic or non-excited state. Very important to note. So reiterating what was stated earlier, one of the important applications of this synthesis is to act as a fluorescent probe to detect important biological molecules such as cholecalciferol, also known as vitamin D, which most people know what it is right here, cholecalciferol. So we have our special profluorophore, which is our molecule that we're trying to synthesize. Then we will react that with a conjugated diene to produce fluorescence. Okay, so down here you see this conjugated diene present in the vitamin D molecule. You got double bond, single bond, double bond. In summary, so to wrap things up, our goal is to complete the final two steps, obviously, synthesizing our target molecule. Right here, we're trying to get here. And then, of course, we're going to continue to study the fluorescent properties of the molecule and its Diels-Alder product, and be able to apply the dye as a molecular probe. Thanks for your time. Until next time.